Hello, everyone, and welcome to Surface Ventures Mini-Symposium on the Tribology of electric vehicles. It'd be great if you could say hi and tell us where you're joining from in the chat today. Great to see so many people have already said hello. Great to see some returning attendees that we've seen before, and quite a few new people as well. So welcome. My name is Dr. Sam McMaster. I'm the content manager here at Surface Ventures. We are a non-for-profit organization, and our mission is to provide world-class surface and materials science education for both academia and industry. Today, we have a number of different speakers, which you can see right here. We're beginning with a presentation from JLR, followed by Professor Ian Sherrington, the University of Central Lancashire. Then we will have a presentation from Brooker, our sponsor for today. And finally, Dr. Nicholas Morris from Loughborough University. I'd like to thank today's partner, Brooker. We'll have a presentation from them later in the event, as said, and we'll be releasing poll questions and handouts from them throughout the event. So I direct you to please answer those. It'd be great to find out more about you as our audience. As we go along, please type your questions into the chat. They'll be marked for the Q&A sessions. We will address the questions for each speaker directly after their talk, and we'll be allocating 5 to 10 minutes for this, depending on length of presentation. As you see, we have 4 talks today, each aiming for about 20 to 25 minutes, and we're aiming to go for a maximum of 2 hours today. We'll be sharing a link for your attendance certificates later in the event. So now, without further ado, let's welcome our first speaker to the stage, Dr. Ali Gambarzadeh from JLR. Ali is a mechanical engineer with over a decade of experience in tribology. He obtained his PhD in tribology from the University of Leeds, where he also served as a postdoctoral fellow and lecturer of functional surfaces. Ali transitioned to JLR as a tribology expert, leveraging his knowledge to contribute to the technical developments in the rapidly growing area of electric vehicles. In his current role, Ali serves as an interface between the development of lubricants and transmission technologies. Welcome to the stage, Ali. Let me just bring your slides up now.
Thank you, Sam, for the introduction.
Thank you for doing that. Take it away.
Thank you very much, and thank you for inviting me to this stage. As Sam explained, I'm Ali Gambarzadeh, and currently a Tribology and Surface Technologies lead at Jaguar Land Rover UK. The results that I'm going to be presenting today is mainly a work within the transmissions team at the Jaguar Land Rover, and in a collaboration with my colleague Matthew Alexander, which unfortunately couldn't attend today's talk. First, I will talk about unique challenges of battery electric vehicles and how the target setting works within the realm of EVs. Talking about electric vehicles, of course, we have to be appreciating the challenges that development of electric drive units are facing in industry. Of course, first thing would be delivering the first attribute and on-road capability of the electric vehicles, which we understand are associated with challenges. Those challenges are different from internal combustion engines due to the presence of different torque and speed relationships, which I'm going to be talking about in a few minutes. But I have highlighted here, for example, the fast acceleration of EVs, which of course apply challenges in tribological contacts. But on top of all these on-road capabilities, our products are also capable of off-road performance. And off-road performance means not only we have to have performance within the defined duty cycles, but there are some other duty cycles that means there's some shock loads applied to our transmissions components. And shock loads means new tribological challenges. In addition to these challenges, we all know that battery electric vehicles are facing some NVH limitations known as noise, vibration, and harshness. In particular, in the transmission development, we are mainly interested in two main challenges known as heterodyne and gear whine. Heterodyne being when two excitations are closely captured, but they are also interacting with each other, and they can cause noise and vibration. And gear whine, which is mainly coming from the contact between the gears in the powertrain, they could be caused because of the transmission error. So it becomes extremely important to design our transmission systems to avoid these NVH problems. Considering the fact that in the internal combustion engine, we didn't have this issue because of the masking noise coming from the engine, but we don't have that privilege in BEV. The other issue is the packaging. So we know that in the realm of electric vehicles, most of the electric drive units are using front and rear units. For front unit, packaging would probably not be an issue because we have the space that is freed up because of the removal of the internal combustion engine. But then in the back, we would have some issues in terms of how to package the EDU, considering the fact that there are probably 7 seats in the interior of the car. So I'm sure everybody has been speaking to colleagues and friends and family talking about, do you want to buy electric vehicles? And the answer would be probably not, probably yes. But the reason most of the customers, potential customers, are not considering EVs is something called the customer range anxiety. So we know that electric vehicles, they primarily have lower range compared to internal combustion engines. For example, if you look at the left-hand side, you see that I-Pace, which is the first generation of our electric vehicles, they had 292 miles range compared to the Land Rover Discovery with 520 miles, which means there's still a big gap for us to overcome. But then looking at the mass and the packaging that defines that range of the car, we can see quite a significant amount of mass is just for the battery. And of course, in order to be able to optimize this system for electric vehicles, we really need to minimize the losses that we have in the electric drive unit, which compared to internal combustion engines, of course, is more efficient, but we're trying to push the limits of efficiencies for battery electric vehicles. I will be talking about the main causes of losses in the next few slides, but what I've put here are mainly the transmission component losses and the e-machine losses, just for example. I think it's a good time to be talking about the main difference between the electric vehicles and the internal combustion engines in terms of how the torque is being delivered within the transmission. So we all know in internal combustion engines, we would need a certain range of velocity to be able to deliver the required torque. And that means over different velocity profile, we really need to change the gears to get to that required efficient torque transmissions. In electric vehicles, that's different. That means we can start delivering the torque at really low speeds, and therefore we can understand the tribological challenges associated with that. And then the torque would reduce with the velocity in order to keep the power constant. So we would have a constant power at the second curve that you're actually seeing there. And of course, we understand that with the new developments within the realm of electric vehicles, we're moving towards higher speeds and therefore new challenges in tribology and tribological contacts that we're facing, which I'm going to be talking about in the next few slides. Talking about design of EDUs and looking at the efficiency of EDUs, if you look at the right-hand side, you would see that EDUs are made out of 3 main components: transmission system, e-machine, and the inverter, each of which have different efficiency profile with respect to the motor speed. If we want to design our transmission system solely based on the efficiency of transmission itself, it means that we are probably choosing something between 10,000 to 20,000 in terms of the speed. But then we have to be very careful that the efficiency of the e-machine increases gradually with the increase in the e-machine speed. And therefore, we have to find a sweet spot for the system where the efficiency of the entire EDU is optimized. And this is why us at the transmissions team are working closely with our colleagues in the e-machine and cascade requirements between the two teams. In the next section, I'm going to be talking about the EDU transmission concepts and a comparison between what we had in ICE and what we're facing in the realm of EVs. Here you can see on the left-hand side an 8-speed automatic transmission, and on the right-hand side a typical electric drive unit transmission. By the first look, you would see that there's probably a lot less complications in development of the EDU transmissions in terms of the architectural complications. Because on the left-hand side, you would see you have clutches that you have to take care of and a very complex lubrication system. On the right-hand side, the complexity has been reduced. There are new challenges that we're facing in development of these gears and bearing systems. They're usually 2 gear stage systems that I'm going to be talking about for different configurations, but we are facing new challenges compared to what we were facing with the automatic or manual transmissions for internal combustion engines. In this slide, I'm particularly looking at 2 common types of transmission system. Left-hand side is the concentric lay shaft or layout, and on the right side, the offset layout. So for the concentric one, you can tell that the e-machine rotor, which is at high speed, it's concentric with the output shaft, which is on the right-hand side. And that means in order to accommodate them both in the same axis, that means our EDUs would be wider. There are some advantages and disadvantages to this configuration. Advantages being compactness of the design, but also wider. Disadvantages, we would, if you look at the 2 gear stages, you can tell that the center distance between the 2 pinion and the gears is the same, which means the second and the first gear stage, they would have the same center distance, and usually the first gear stage is not optimized for the performance. On the other hand, on the right-hand side, you can see the first rotor shaft being connected to an intermediate shaft, and then intermediate shaft with the gear stage 2 being connected to the differential and the output shaft. In this case, you could have a better control over the design of your bearings and gears and their sizes. And of course, your EDU would be larger and would have a higher volume. So that's the trade-off between efficiency and the packaging. The next transmission concept is the planetary concept, which is probably the least common among the 3. The reason for that is there are quite a lot of challenges associated mainly with the NVH problems and the efficiency of the system. NVH because you're having a sun gear in the middle and 3 planetary gears in contact at the same time with that, which means you would probably look into some heterodyne or gear wind issues because of 3 contacts happening at the same time. And of course, you would have more contact happening, therefore more frictional losses, which is unwanted within the EDU, and we are working hard towards efficiency. Therefore, that would be a challenge for us. So now that we have talked about different configurations of the transmission system and everybody understands what components we have within the system, now let's talk about the main EDU losses, and I would then dive deeper into transmission losses, which tribology would play a great role in. So if we look at EDU, we said it's made out of e-machine, which is motor, inverter, and the transmission. Of course, some low voltage components such as the oil pump and the valves and some other components that are consuming the power within the EDU. For the E-machine, the main losses are mainly electrical related losses, such as iron losses and copper losses, but also we would have the shaft rotating at high speed, therefore we would have some drag, friction and windage. What I'm going to be focusing on today would be mainly around the transmission losses, which are our tribological losses, mainly due to the gear mesh, the bearings, and the dynamic seals. I wouldn't focus today on the dynamic seals because that's the least out of these three. But of course, our gear also experiences churning and windage losses as well. We need to understand that within the EDU, we would have different shafts rotating at different speeds. Therefore, selection of gears and selection of bearings based on their performance becomes extremely important to avoid the not efficient operation of the components. In the next slide, I'm going to be specifically talking about the gear mesh and the bearing and some of the challenges and what we think are the solution to those challenges. But before talking about it, I'm going to be drawing your attention to the Strybek curve you see at the bottom of the screen, where we can plot the coefficient of friction against the Sommerfeld number. I haven't included the Sommerfeld number and just put down the speed, just to compare the electric vehicles and internal combustion engines. So there are few things to consider when we shift from ICE into EVs and in terms of tribological performances of our components. The main two probably being the torque speed, but also we have to consider the fact that our lubricants are lower viscosity lubricants in the EDU. So E-fluids are usually a lower viscosity, so I'm going to talk about them later. Understanding that for the same speed, you're experiencing an extended boundary and mixed lubrication regime. And therefore, our gears and our bearings, they have extended more severity of contact, which should be taken into account. So just to highlight the challenges we're facing within the contact of bearings and gear mesh is, of course, the high speed we're experiencing for our bearings and gears, and that means high contact temperatures and high thermal losses. Our lubricants are low viscosity, of course, but one property of the lubricant that needs to be greatly taken care of is its copper compatibility because of the presence of E-machine. And remember, if you're using the same fluid to cool the E-machine, the fluid has to be copper compatible. I'm going to be talking about the challenges of copper compatibility in the next slide, but that means that our additive technologies, they have to have low amount of corrosive agents to metallic surfaces, and that expose a lot of challenges for protecting the surfaces. I have highlighted three main failure modes that our gears are experiencing, known as scuffing, bending fatigue, and micropitting, each explained in the text. But there are routine surface treatments to increase the efficiency of these components, but also their durability. Of course, heat treatments are conducted to increase the toughness and the hardness of these gears and components. Super finishing, although expensive, that's an important surface treatment for us to reduce the contact, reduce friction, and of course, thermal dissipation at the interfaces, therefore reducing scuffing and micropitting. Again, although costly, coating technologies could help with reducing friction and increasing the scuffing and micropitting performance of the gears. And of course, shot pinning being something that the gear industry has been doing for quite a few years. Talking about the contact, of course, we would have lubricated contacts within the EDU, which means the lubricant would play a major role in the tribology of electric vehicles. I have written a text here saying that EV fluids are fundamentally different from traditional driveline fluids, which is, I think, very important for everybody to understand. We are not continuing with the previous technologies, and we are having a completely different formulation because of the web diagram you see on the left hand side. These are the new requirements that e-fluids need to have, that I'm going to be cherry picking some of those in the next few slides to talk about some of these requirements and the importance of them. But I have picked one of them in particular, and that is the copper corrosion compatibility. And the images you see there, if we actually, there's always a balance between copper corrosion and wear and scuffing on our gears and our bearings. It's really important that we find that sweet spot, because the same additives that are not corroding copper, they are protecting the gears and surfaces from wear, and it's really important to find that sweet spot. And there's a big demand for OEMs and lubricant suppliers to understand this region of application for extreme pressure and anti-wear additives. In this slide, I would be talking about electrical conductivity. We all understand that within an EDU, there would be high electric field and high magnetic fields. That means that lubricant should be compatible in this scenario, which means we want lubricant to have certain electrical properties. Lubricants should be dielectric, which means it's really important that they have certain electrical resistivity. We want them to have high resistivity, but we don't want the resistivity to be too high, because if they don't dissipate charges, it means that charges are accumulated and lubricant additives are degraded. So that is unwanted. So there is actually, again, a range of electrical conductivity that we would like to see. And if the electrical conductivity of the lubricant and the dissipation factor are not working well, you would see all sorts of problems within the EDU, such as additive degradation, bearing and component damage, electric discharge, etc., etc. And I have put an example of a test that we conduct to understand the behavior of these lubricants on the high voltage scenarios known as breakdown voltage. It's an industry standard test where you put the lubricant and you apply high voltages around the lubricant to understand how the lubricant would break down or how it would degrade on the high voltages. Talking about some of the properties of the lubricant, of course, we still want the e-fluids to show great extreme pressure anti-wear properties. Being a leader in the industry for off-road capability, JLR differential scoring test is something that we really need to pass to be able to filter the lubricants. So if lubricants have all the properties and they're singing and dancing and fantastic in terms of their copper compatibility and all the other performances, they also have to be passing quite a strict differential scoring test. Basically, testing on our setup with our duty cycles in terms of the load and in terms of the speeds, and then taking and visualizing the differential internal components, especially the crosspin, to look at the wear of the crosspin, and the lubricant play a major role in protecting these components. Last but not least, we have worked hard to understand how these new additive technologies work within our transmission system in terms of the friction, and the friction properties are of great importance to us. Of course, we want more efficient transfer of power. So we have been running a large number of tribo tests with the help of our suppliers to understand in rolling sliding and in pure sliding contacts, what are the friction coefficients of the current lubricants and the lubricants that we're developing with our suppliers. And on top of that, cooling performance of our lubricants become really, really important because of the high speeds in bearings and in gears, therefore cooling them off. But not only that, it's the e-machine that has to be cooled off if you're using the same lubricant for cooling of the electric motor. At the bottom, you would see a viscosity ladder profile. just highlighting the fact that traditional axle oils were about 15 centistokes, transmission oils about 9 centistokes at 100 degrees C, and current e-fluids are less than 6 centistokes. I want to show the level of decrease in viscosity of the lubricants, and this is obviously evolving currently. But we have to be very careful. It's not only about the losses in the gears and in the bearings, it's also about other system attributes and performances, and you have to be really taking care of the aeration and the foaming properties of the lubricant at low viscosities. Thank you very much, everyone. Thank you for listening, and you're all more than welcome to ask questions.
Thanks, Ali. Great presentation. We have one question. It's multiple questions here from Fabian, which I'll bring up now. So he asks, regarding the reduction of friction losses in gears, can you give more details on the specific coatings you would apply? I guess let's go through each of the questions as.
Sure. Yeah. Well, I think what I can the information I can give here is very limited, Fabian. But this is a nice question. I think if you review literature, you will find some of the coatings that are most suitable for gear applications. It's a challenge because gear applications with coatings, it would be difficult to keep the coating on the gear. And if you review literature, everybody is talking about DLC and WCC and all these coatings, but then how would they work on a gear at high speed? I think that would be the challenge. But there are a variety of coatings that could be used for high speed gear applications.
Thanks. Okay, so next part of the question is, which one of the mentioned measures do you regard as being the biggest lever for reducing frictional losses?
Really, really good question. So I think it's really important here to distinguish between the losses. We have load-dependent losses and non-load-dependent losses. If you're just talking about load-dependent losses that happen in the bearing and in the gears, bearings are mainly showing losses at high speeds. And therefore, when you're working at high speed, irrespective of the torque that is applied, bearings are dominant loss components. For gears, you mainly have the contact between the two gears at the mesh, which means you probably have at low speeds and high speeds the contribution of losses. So we can't really say which one is the biggest lever, but what I can say is it's a combination of the two, and at different torque speed combinations, you would see different behavior. Sometimes your bearing losses and bearing chaining losses are the highest at high speeds, and sometimes you have the gears at the gear sets with higher friction losses.
Okay, thanks. And then the final part of Fabian's question: do you consider gear tooth geometry as well for reducing friction losses? Absolutely.
I think that's super important. So gear geometry not only important for reducing NVH, as I talked about the gear wind and heterodyne, but it's super important on the pattern of contact on the gear flank and therefore friction losses. So there is a lot of work done on understanding these patterns and how surface super finishing or other technologies could reduce friction losses.
Okay, thank you. We've got okay, so we've got a good few other questions coming in. So let's try to get through a few of these in about 5 minutes before we move on to the next presentation. Yeah. Sorry for everyone in the audience. We're going to have to be a little bit selective with questions, but Ali, if you're here, be able to stay for the event and able to answer some of those questions in chat, that would be great. Thanks.
Sure.
Okay. Emmanuel has asked and said, excellent presentation. Is thin film coating an area of science considered by JLR in the area of improving the coefficient of friction for load-bearing applications?
I'm not really sure what thin film coating we're referring to here, but if you're talking about the a few micrometer coatings on the surface of the gear, this is what literature has been showing that shows some improvement. And I think yes, automotive industry in general may consider thin film coatings for gear applications.
Yeah, I think any questions like that, they're probably referring to your sort of PVD, CVD hard coatings. I would probably, unless there's something a little bit more exotic out there. Ray, I hope I'm pronouncing that correctly. I said, great presentation. Are JLR considering the use of hardware strategies to limit the electrical discharge currents?
Really interesting question here. So with electric discharge, I think everybody is learning a lot how to minimize the discharge. And to answer the question, yes, I think it would be for the foreseeable future. Everybody unanimously agrees that it's not only the lubricant that can help. We should also consider the hardware strategies, because at the end of the day, you have electrical and magnetic fields, electrical fields, and electrical current is there. You have to find a pathway for the current to be going out of where it is from the rotor. Therefore, yes, but we are also working with our lubricant suppliers to understand how lubricant could actually help dissipate those charges.
Okay, that's great. Thank you. There's 3 more questions in the chat, but I'm afraid if we stay too long on questions, we're going to run over time with our other speakers. So, Ali, if you're able to answer some of those in chat,
Sure.
that would be great. Thank you so
Sure.
much. Thank you again for your excellent talk. We're now going to move on to our next presentation.
Thank you all.
Okay, thank you. Okay, our next speaker is Professor Ian Sherrington, who is a professor of Tribotechnology and director of the Just Institute for Tribotechnology at the University of Central Lancashire, and an affiliate professor of Tribotronics at the Royal Institute for Technology in Stockholm. He's currently chair of the IMechE Tribology Group Committee and executive director of the International Tribology Council. His research activities center around the development methods for prediction, measurement, and control of tribological parameters. Ian, welcome to the stage. Excellent. I can see your slides now, so please take it away.
Thank you very much, Sam. Good afternoon, everyone. What I would like to do today is talk about how to model friction in electric powertrain. And the model that I'm going to present is a general model, so it's not specific to electric powertrain. It can be used in other components too. Before I start, I'd just like to thank a couple of people and organizations. First of all, my colleague, Professor Ian Taylor, formerly of Shell Global Solutions, has processed all the data which I'm going to present today. So thank you to Ian. And also I'd like to thank those who supported the work, in particular this Japanese organization, TTRF, who provided funding for some of the analysis. And some of the data was provided by the Tribology group at Imperial College London. So thank you for that kind support too. The presentation will break down neatly into 2 parts. Just got a pointer here. The first part will discuss some background on electric vehicles and electrical vehicle fluids. And the second part will present this friction modeling technique. Essentially, what we've noticed is that approaches to mixed and boundary friction modeling either tend to be extremely simple or extremely complex, and in some cases generally erroneous as well, so they don't give accurate data. So what we've tried to do is to produce a compromise model which will allow accurate, simple modeling of mixed and boundary friction components, and you'll see why this is in some detail as we go through the presentation. So just by way of background, everybody's aware that the electric car stock globally is increasing substantially. And in 2022, there were 26 million electric vehicles, but that's only between 2 and 3% of all electric, all cars that we use, all passenger cars. And it's important as well to realize that nearly half of those are in China. China is a really big player in the EV market, not just in passenger cars, but also in buses. Several 100,000 electric buses operate in China. Although the growth of electric vehicles is rapid, there are some considerable challenges, considerable engineering challenges that are being faced by this industry. And Ali mentioned some of them, but I'll mention some of them again. There are issues, first of all, connected to manufacturing infrastructure. If we want to replace all the internal combustion engine vehicles that we produce by EV vehicles, we need to considerably up the game globally to produce manufacturing infrastructure that's suitable for this kind of technology, and particularly the batteries. The battery technology is well recognized as something that needs to rapidly improve. Ali also mentioned range anxiety. So in addition to that, not just is the range short, but the charging infrastructure is, generally speaking, quite poor. It's hard to find somewhere to charge your car away from where you live. And it can take quite a long time. There's also an elevated purchase cost. And if this doesn't change, it's going to restrict uptake of EVs because not everybody can afford an expensive EV. Then there are kind of geopolitical problems. So sourcing battery materials tend to come from non-Western sources, and they're processed largely in non-Western countries as well. So gathering these materials from the environment, processing them, and producing the materials that we need to make batteries is a significant challenge. And then I guess a purely engineering issue that, again, Ali mentioned was that we get vehicle noise, so particularly gear whine is something that perhaps we might like to get rid of. There are certainly considerable advantages from EVs, and here are a couple of them. So from an energy perspective, they're extremely efficient. Well over 90% of the energy that we put in is converted into useful power, sometimes as much as 98%, and their CO2 output at the point of use is basically zero. We have two common types of EV, battery electric vehicles and hybrid vehicles. And compared to internal combustion engines, EV fluids need additional capabilities. So for example, they need high thermal capability. You might argue that IC engines also need fluids with high thermal capabilities as well, but it's different for EVs because quite often they're filled for life. So we need to keep the operating temperatures very low to prevent lubricant degradation. We need to have high thermal conductivity to take the heat away from the mechanical elements that we want to cool. As one of Ali's slides ably demonstrated, there's a challenge here because the thermal conductivity and the specific heat capacity are in direct opposition. So as we increase the conductivity, the thermal capacity tends to go down. We need compatibility with copper, and we need fluids that have high load carrying capability. So the greatest torque appears at the lowest speeds with the highest loads, and we need to manage the high stresses that places on lubricants. And there are lots of other requirements as well, resistance to foaming and so forth. There are a whole host of tests that we can apply to these fluids to see whether they're suitable for a particular application. This is by no means an exhaustive list, but here are some of the tests that are required for wheel bearing lubricants. We need to make sure that these fluids pass these various tests, and the suppliers, of course, the suppliers of the fluids have a significant challenge to make sure that these tests are passed in all cases for all vehicles, in the same way that we've developed these kind of global lubricant tests for internal combustion engines. And of course, to maintain the efficient operation of EVs, these fluids must have low friction. And in the same way that we want to predict the range of IC engines, we might want to predict the range of EVs. And this is important because it allows us to understand what the theoretical operating range is going to be, what the charging requirements are going to be, and to some extent what the ownership costs of this vehicle are going to be from an operating perspective. Modeling fluids has been done for a long time. Modeling contact friction has been done for a long time, and we have used various kinds of models for this. So hydrodynamic models and EHL models are well established, and running alongside that, boundary mixed friction modeling is not so well established. And what we find in this instance is that these models are quite often, as I mentioned earlier, very simple but not very accurate, or complex and difficult to implement. And what we want to do with these models is to try and understand the Strybek curve, try and predict the shape of the Strybek curve, so that we can use data that we can easily get our hands on, either these duty parameters or the lambda ratio, and understand what kind of friction may result from one of these contacts. Why is that important? Well, for a long time, internal combustion engines have been modeled using hydrodynamic lubrication. My feeling is that this has been done because it's comparatively easy to do. So full fluid film lubrication models are very common. Lubrication models which also incorporate mixed and boundary lubrication, less so. And I think it's tended to push us in the direction of believing that actually mixed and boundary friction isn't particularly important. And I think it is. I think it could be quite a significant oversight that we've made in our modeling of all kinds of mechanisms. There's a couple of examples here. The first one is this axle mechanism. You can see that there are two power loss columns here. So without the boundary modifier, the power losses are given in this column here, but with the boundary additive, reducing the friction, you can see the friction comes down enormously. So obviously it's speed dependent. So faster speeds, the difference is less when we get a more complete fluid film. But at lower speeds, we get quite considerable changes when we introduce this boundary additive. That means that boundary friction is present, and that incorporating the additive brings this significant gain in reduction of friction. Similarly, if we look at other components, so needle roller bearing here and a bearing hub unit, you can't see this number on here, but it's 55%. And this is a significant, these proportions here are a significant proportion of the losses in these particular types of component. And so if we don't model these, we miss quite a lot of the friction contribution that we should be seeing in our models. So as I've said, friction coefficients can be modeled. We might use linear models, or we might use quite complex models that involve predicting the deformed real contact area using various kinds of surface contact models. So Williamson trip, for example, Greenwood trip rather, and average flow modeling to get flow coefficients for the lubricants. So they're either simple in the case of linear models, or complex and not easily implemented. And what we wanted to try and do is to put together a model that, if you can calculate the lubricating film thickness in a contact, then you could very quickly, perhaps in an hour, build a little spreadsheet or something to predict the boundary and friction power losses that go along with that. So this is how we went about that. Most of you will recognize this. This is the lambda ratio, and we can characterize the various regimes of lubrication, boundary, mixed, and hydrodynamic, by taking the ratio of the film thickness and the square of the RMS roughnesses, or RQ roughnesses, if you like, adding them together and taking the square root. And by looking at the ranges of the resulting parameter lambda, we can determine which regime of lubrication that we're in. So boundary, mixed, or full fluid film, as we work our way through the Strybek curve. Very commonly on the bottom, we've got duty parameters here, which involve viscosity, load, and speed. However, we can replace this axis with the lambda value. So as the lambda ratio increases along the x-axis from 0 to, let's say, 3, we can move through the various regimes. There are some flaws in this theory, and I'm going to mention them before we get to the end. I'm going to mention them now so that you understand that I appreciate them. The first one is that this equation only applies for 1D roughness. It doesn't incorporate surface data, a real data information. There's no surface character data, so surfaces with different topographies can have the same RMS value. That's a flaw in the arrangement. There's no lateral data in the model, and the ranges that are selected here, they're arbitrary. They're really selected around the idea that the surface topography would be randomly distributed, and if you get more than 3 standard deviations away from the mean, then it's very likely there will be contact between the surface asperities. So this is the method. Normally we can start off with some measured data or a Stribet curve like this. It doesn't need to be our own data. It can be data from someone else's work. And what we suggest is that this friction data, this Stribet curve, is normalized to produce a parameter x, which varies between 0 and 1, and tells us the proportion of mixed to boundary lubrication. And we can normalize it by dealing with the y-axis here. We can subtract this fluid film friction from the boundary film friction to generate a number which varies between 0 and 1 if we subtract this limit down here from the friction at the point of lambda where we want to operate. And what we find is that this equation for x, if we adopt real data like this, turns out to be very nicely modeled by this equation here. So this is the equation for a sigmoid curve. And essentially, we can model this equation by considering just the lambda ratio and these two constants k and a. In our measurements, we found that k is 3/2 and a is 4/3. Once you've got this data, you can very easily then calculate the friction losses in a contact, provided that you know what point in the lambda range your contact operates. And you can get this by predicting the film thickness and dividing it by the sum of the RQ values squared, square rooted. Here's our evidence. So these data points in this graph are placed on a graph like the one I mentioned. So lambda ratio across the x-axis and the ratio of mixed to boundary lubrication of the y-axis. All of these data points are taken from published data. So this is not our own data. This is data that we've collected from other publishers. And we did notice straight away it's quite difficult to acquire. We were specifically interested in trying to get hold of run-in data, so that this is data that is stable. It doesn't change anymore with the operation of the machine. So it's quite easy to get data off this curve, but not for data that's run in. We also see that we've got more data at low lambda, and so this fit curve that we've created, the green line, is somewhat distorted because it fits better where there's more data, and it doesn't fit quite so well where there's less data. So we recognize that. The great thing about this curve is that it's got full range applicability, so it will run us straight from boundary lubrication through to full fluid film lubrication. And we have asymptotic convergence between the various regimes, which you don't always get if you use other models. And finally, one of the nice things is that this is for lubricants that don't contain additives. It also seems to collapse reasonably nicely onto one fit curve, which is convenient for modeling. If we compare the friction coefficient prediction, or let's say the degree of mixed and boundary lubrication with the lambda ratio for a range of different models, we see something interesting. So here's the green line, which is our our model here. And if I take, for example, the Greenwood and Tripp model, which is probably one of the most commonly used models, you can see there's a significant difference between the two models. If we look at a particular lambda ratio, let's take lambda ratio 1, you'll see that the amount of bit mixed and boundary lubrication predicted by the Greenwood Tripp model is, about 90% hydrodynamic. But on our model, which remember fits the data curves, it's more like 70%. So the Greenwood Tripp model, you could argue, significantly underestimates the amount of mixed and boundary lubrication for quite a lot of this range. Of course, many lubricants contain additives, and two of the most common additives are friction modifiers and anti-wear additives. They work in slightly different ways. So friction modifiers form molecularly thin layers on a surface and reduce the friction coefficient in the boundary regime. So if we look at our Striebeck curve, the low lambda end of this curve comes down. In the case of anti-wear additives, the way that they work is they produce this kind of thick-ish sacrificial film on a surface, which is continually deposited and worn off again to protect the surface from wear. And as that happens, it makes the surface somewhat rougher. So it's equivalent to sliding the Striebeck curve to the right of this graph. We can take account of both of these effects in our model. Oops, I beg your pardon. By incorporating an extra coefficient here, so this parameter C will allow us to deal with the change in the boundary friction coefficient. And then the data that we collected, for which I'll show you in a moment, C was about 1.5, 1.6. And we can deal with the change in roughness by also always using the run-in roughness with the addivated surface being used to predict measure the addivated surface roughness in creating this parameter x prime. The rest of the process is exactly the same. How well does that work? Well, here's some published data from 3 oils, which we selected for our analysis. And here are the fit curves to those 3 oils. So you can see that the fit isn't perfect. There's only one set of data. And one of the key things here is it doesn't all collapse onto a single curve either, which is slightly inconvenient, but nevertheless still a lot simpler than addressing the problem by using surface modeling techniques. So our argument is that this technique also can be used for addivated lubricants as well. It's just that you need some data for each lubricant that you want to test in order to be completely certain that you've got a good idea of the fit. So moving towards a conclusion, for oils without additives, we believe we've got a really quite accurate model for predicting friction in the boundary and mixed regimes. It's quick to implement, it's easy to use, and it appears to be accurate because it's based on obviously experimental data. We can also model modified oils, addivated oils. They don't collapse onto a common curve, but you can still use the same technique provided you've got data on a case-by-case basis for each lubricant. We're going to carry on with this work, and there's something in mind, something important that we have in mind. Climate action and responsible consumption and production are critical to the future of the planet. We live in a time where we've got a climate crisis, and as engineers, we have a responsibility to support sustainable growth and the development of a low carbon transport and infrastructure for the future. In the same way that we've spent a lot of time accurately modeling internal combustion engine vehicles, what we'd like to go on to do is to produce models that allow us to understand how HEVs and BEVs would behave in theory, using friction modeling of friction losses and mechanical components, all of them in the vehicle, by understanding auxiliary losses, by incorporating tire road friction, aerodynamic losses, affected battery mass, and so on. We're looking for partners for this, so if you're out there and you're interested in talking to me about this, please send me an email and we'll be very happy to discuss collaboration with you. And just as a closing slide, I'd like you to think about this. This is a quote from Robert Swan, who is an Arctic explorer. "The greatest threat to our planet is the belief that someone else will save it." I don't think we can rely on politicians to save the planet. This mission is for engineers. We're the ones who implement the solutions. We're the ones who create the solutions. And if we're going to do anything effective, then we need to work effectively as a community. Tribologists are in a unique position. We look after both power loss and the lifetime of machines and components, and we should work diligently to try and meet this objective. Thank you very much. I'll be very pleased to take any questions.
Thank you very much. Great presentation, and very poignant final slide. And very good point there. We've got one question currently typed into the chat, so let's begin with that from Ben, who asks, with respect to your modeling equation, does this equation only work for liquid lubricants, or would it work for greases also?
That's a good question. I would expect it would work for greases, but greases don't necessarily behave like fluid lubricants because they've got more than one component in there. So if you look at the behavior of greases, it can be really quite unusual. We've not done any work with grease data, but it is certainly something that would be an interesting thing to look at. So I'm not going to confirm that it will work. I think that's an open question.
Okay, thank you. Whilst we're waiting for any other questions from the audience, one of the points you raised was about the actual difficulty of getting data in order to base some of these models on. Was that in reference specifically to the testing that you would need to perform in order to get this data, or the fact that as a sort of research community we are quite bad at sharing our data openly?
I don't think it's necessarily a question of being open. I think it's a question of being complete. So the kind of data that we need for these to do this analysis, we need surface roughness data of a particular sort. So we always need to be able to see the RMS values and the friction measurements, and they need to be run in. And finding that combination of data seems to be quite important. And I think the short answer to your question is yes. I think we are quite poor at sharing data, and that is partly because we have all these different approaches to presenting the data, which are often specific to a given research group or specific to a particular topic discipline, and some uniformity would certainly help. I think as we move forward, the availability of data with open access policies is increasing, but nevertheless, it's still tricky to get exactly what you need. And we don't actually own an MTM machine, so that's one obstacle for us. So we can't do our own experiments to check these things out.
Yeah. Yeah, no, that's a good point. I mean, I think it is good to see a lot more open access becoming adopted. So hopefully it will be easier in the future with this. We have another question from Shirish. I hope I'm pronouncing that correctly. Apologies if not. Another question regarding the equation, asking if this could be used for valve train friction modeling.
I don't see why not. Yeah, I think provided you're clear about whether you've got adiuvated or non-adiuvated lubricants, I think this could be quite a successful way to approach that problem. Certainly. Yeah.
Okay, thank you. And then we have another question from Peter here, asking, what about additive compositions? I guess that maybe with regards to modeling different additive compositions.
Well, the question's a little bit ambiguous. It depends on the additive. So friction modifiers probably easier to incorporate than wear modifiers. Essentially, you need to think about what classification of additive is it, and how to deal with that in terms of, does it affect the boundary friction coefficient, or does it change the roughness? I've no doubt there are additives that do both of those things as well. So you need to be careful about how you treat the data. So if it changes the boundary friction coefficient, then you need to introduce that coefficient C. And if it changes the roughness, then you need to incorporate the modified roughness, the roughness that's generated by the additive, in calculating the combined roughness of the surfaces before you apply the curve. But in general, at least for the additives that we've looked at, it seems to be okay.
Okay. Thank you. I have a final, we'll take this as a final question for Ian from Sang here, who says, thanks Ian for a great presentation. I'm wondering whether the equations you proposed can be used as a generalized approach for different lubricants, especially with many new types of lubricants like ionic liquids or liquid crystals, etc., with uncommon behavior during sliding.
Okay. I don't know the answer. It's a bit like the grease answer, really. Some of these fluids can be actuated by the electronic structure of the surfaces, or deliberately applied surface potentials, and their behavior, whilst being predictable, isn't necessarily easily incorporated into this equation. I think if we take ionic liquids as an example, there's a possibility that there will be described by the basic equation. I'm not so sure about liquid crystals because they are orientation dependent. The components are orientation dependent. But again, it's something that will sit in the future work portfolio. I think it's something that we could look at.
Okay, thanks. Yeah, be quite interesting to see where this project goes in the future. Okay, thank you very much, Ian. I think with respect to time, unfortunately, we're going to have to move on. Although, one quick comment there from Peter regarding his question about additive compositions. He says, we simply don't know what the additive compositions are. As an example, Mobile 1 varies from year to year.
I see, right. Okay, so when you get a commercial lubricant, you don't know what's in it. Yeah, I understand that. Sorry.
Yeah.
Well, provided that in the example that I showed, provided you know that it's a friction modifier or wear modifier, you can classify it. You could do an MTM test, collect the data, and model against it, but you wouldn't necessarily understand the amount of that additive or what that additive was. You don't need to know what it is or the amount of additive in order to do the modeling. I understand.
Yeah. Okay. Great. Thank you very much, Ian. Great presentation, and thanks for answering those questions. We will now be moving on to our presentation from Brooker. Two presenters here. first of all, is Sandra Bergman, who's a product line manager of the optical product line for Bruker Nanosurfaces and Metrology, and has extensive experience in the non-contact measurement industry. Additionally, we have with us today Roger Posusta, who is a senior marketing application specialist at Bruker Nanosurfaces Metrology division, and he has over 35 years of work experience in metrology. He's the co-author of 2 patents related to metrology measurement. Roger will be joining us later for any applications related questions. For now, let me bring up your slides, Sandra. Just before you begin, I just want to highlight you are currently muted. You're good.
Thank you, Sam, and thank you for the introduction.
Thank you.
So, hello and welcome to a talk about our electrical vehicle surface metrology. So, first of all, let's take a look into the outline of this presentation. So, in order to ensure the overall electrical vehicle performance, the inspection of surface finish and the coatings of EV battery and the vehicle conduction chain is critical. So we will discuss the inspection of these important parts by measuring non-contact white light interferometry, short WLI, which is also known as coherent scanning interferometry, short CSI. And to underline the importance of the non-contact inspections, to ensure this performance of EV, we will focus on the key areas of characterizing surface finish and detection of defects, corrosion prevention and detection, uniform coating characterization, conductivity with enhanced thermal management, and in the end, we will shortly go into the 3D analysis parameters, and we will also go into the theory of white light interferometry and the advantages of it. Of course, all the topics are very wide, and we could fill days of it. So in case you want to have a little bit more details, please don't hesitate to contact us. Also, you use the question possibilities, but you can also contact us after this presentation directly. So let's go first into the characterization of surface finish and detection of defect. So why is the characterization of the surface finish such a critical part? And why is it such a key role? When it comes to the electrical components, such as electrical contacts, for example, in battery, the cathodes and anodes, connectors, switches, and circuit boards, the surface itself is directly, or the surface directly affects the contact resistance. This means a smooth and clean surface finish promotes a better contact between the conductive materials, but also reduces the resistance, which leads to improved conductivity efficiency and a lower component temperature. In comparison, a rough or uneven surface results in smaller contact areas, which can lead to higher resistance, reduced conductivity, and is also increasing the component integrity. So hence the inspection of the surfaces assure the performance of each component. And here WLI, white light interferometry, can provide you a high accuracy and non-contact method to validate your surfaces without any impact by the measurement itself. A further advantage of this is, or of this technology and method is that by using the same 3D image of the surface we are measuring, you can detect and characterize also defects and not only do one measurement at one image. And when we take a look at some examples, this is a very great example where you can see a highly pitted surface, which is pitted from a cleaning process. And this pitted surface can lead to or can cause poor contact. When we are measuring now with WLI, we can fully automatically measure the surface itself, but then also analyze and detect the bits and then get a full overview of the quality of the surface. Our next example here shows the automatic measurement of contact pads. So contact pads needs electrical tests, which are commonly executed with electrical probers. These probers can leave prober marks, or not only can, they will leave prober marks on the surface. And for example, if you have a damaged prober tip, these marks can have a negative effect on the contact pads. So with WLI or with non-contact measurements, with WLI, you can automatically measure the prober marks, analyze the volume of the prober marks, and then receive the information if the prober mark will have an impact on the functionality itself. The next example on the surface finish itself illustrates the measurement of large EV battery canisters. The surface finish of the sidewalls as well as the bottom of the canisters have a direct impact on the functionality, but are very difficult to access with metrology systems or with metrology itself. What we can do is we have unique objectives. For example, as you can see here on the first right-hand picture, so-called borescope objective, where you can access directly into the canister and then measure the vertical sidewall of it and check on the surface finish of the sidewall. Furthermore, you can. It is very difficult because the canisters have a certain size or height. So if you want to measure the bottom of it, you also need certain objectives. Like we have very long distance objectives where we can then reach down to the bottom and check how flat it is. Are there any things that prevent the surface finish to have a good contact? A further key topic in EV is also the corrosion prevention and the detection of it. So corrosion itself can weaken the battery casing and of course the battery material itself, which can then lead to leakage of electrolytes, decreased battery efficiency, and it can also shorten the performance and also the lifetime of it. So furthermore, corrosion can also degrade the conductivity and can form insulating layers, which also increases the resistance of any contact. So in this case, the detection and addressing corrosion at a very early stage, either during the research and the development or during the quality inspection, highly improves the performance and the lifespan and the lifetime of the battery itself. So therefore, this surface measurement with WLI can really indicate and assist you in the improvement of the protection against corrosion of your parts. On the next slide, you can see here a very nice example of a fully automated measurement, which checks on material changes. So this can not only be used for detecting corrosion itself, but also for the analysis for further information on the material changes, which can occur through corrosion or through any processing or through any process or processing of the material. So as a result, you can receive a complete quantitative characterization of the surface. A next key topic is the uniform coating characterization. So a consistent and uniform coating in the battery and in the electrical component surface is essential for efficient performance and isolation. So coating needs to be applied evenly, which then prevents missing areas or excessive thickness or thinness, which all can lead to reduced performance or degradation or a shortening of the lifetime of the battery. So with WLI or with the technology of WLI, you can either measure through transparent or semi-transparent coatings, or you can measure the coating step from the bare material onto the coating. And when measuring through the coating, the thickness can be measured anywhere on the surface, allowing inspection of the top and bottom surface coating along the whole thickness uniformity. The big advantage here is also that when you're using WLI in contrast to any contact method, is that the surface itself, for example, when it does not get manipulated or changed or damaged, and this is especially important when you have flexible coatings or any coatings that cannot be touched or changed or transformed by the measurement itself. So let's now take a quick look at the theory of how we are measuring with WLI the thick films or the films of materials. So for measuring a transparent or a semi-transparent film, we measure a step from the top of the film to the bare substrate. And then the maximum measurable thickness is only limited by the scan length of the profiler you're using, which is in our case 10 millimeters. So this is the maximum film you can measure. The minimum reachable film is between 50 to 100 nanometers, which is more or less limited by most of the films or the film materials, because below that area or below that height, the films are not opaque anymore. So on each coating interface, as you can see here, so on the top of the coating or the top of the film, as well as the interface of the film and the substrate, you can get the information, the fringes, and from that you can derive the thickness of the film. A further big advantage of this way of measuring is, as you can see it here in this example, is that not only the thickness of the film can be measured with all the parameters like average and roughness parameters of the film. You can also get within the measurement the top surface, the surface itself of the top, as well as of the bottom. So you can also have here the information along the whole film thickness measurement and get all the detailed information about that. And in case if you want here some further information on film measurement, you can also find then afterwards in the symposium some in the download area an app note about film measurement. But now let's jump into the conductivity with enhanced thermal management. So surface inspection can also improve the thermal management of the battery heat dissipate components. This means the irregularities in the surface finish can hinder heat dissipation, which leads then to overheating, which then also leads to reduced performance. So a smooth and uniform surface finish definitely helps you in efficient heat transfer. The quality of conductive surface finish, depending whether it's smooth, matte, rough, roughly textured, directly impacts the distribution of the current across the whole surface. And most of the time, plating the surface with a metal coating is a very typical way to enhance the electrical conductivity and to inhibit also corrosion. So a smooth, highly quality finish indicates always fewer surface irregularities, also allows you for more uniform current flow, and minimizes the points of the high electrical resistance. While in comparison, a rough or uneven finish can lead to localized areas of poor conductivity, potentially affecting electronic or electrical system performance. And in the next slides, you can see here some typical measurement results of machined surfaces. So you can see here some flat lapped surfaces, milled surfaces, turned surfaces. And as you can see, the surface itself looks all the same. But of course, the roughness itself, which is a very standard parameter, the RA, which is the mean roughness, shows in some cases, like on the very right side, on the turning and the vertical turning, they show the same RA value, but the surface itself looks different and would also need either a different coating or a different way of coating, or they would also have a total different conductivity. On the next slide, you can see it even more detailed or more clear. We have here totally different surface finishes, a total different way how this surface would lead the current or would distribute the current, but it has the same RA value. And to the RA value, we will come a little bit later in the next slides. Here's just another example of using also our software to check on the appearance of some material. For example, if you have paint, there is some very typical finish that always fails or wants to be avoided. This is the so-called orange peel. You can see here on the right hand side, you can see a 3D image of the typical orange peel, which always leads to not very good appearance of the paint. And by using our 3D spatial frequency parameters, we can check also on painting, so the appearance, and check on when it passes or fails in terms of appearance or other parameters you want to take a look at that. So now you have heard a lot already, a few of these analysis parameters, and in the next slides we would like to get a little bit of a closer look at them as a short overview. So in order to characterize a surface finish or a surface topography, there are three main characteristics used. One is the roughness, then the waviness, and also the lay of the major surface features, which is nothing else than the direction of major surface features. So roughness and waviness are the two main characteristics to observe and control, for example, friction, and the surface formation caused by sliding, wear, coatings, or lubrication retention. Both characteristics are also well established for qualifying the visual appearance, for example, like in paintings. Also, each manufacturing process of the material produces a certain surface texture itself that can be described by different surface textures parameters. And on the right side, you see table with very typical machining processes and also their expected corresponding RA mean roughness value. And here you can see it for metal cutting, what is the expected roughness, for example, milling, for abrasive materials, casting, forming, or others. So when you see all these different applications, which application parameters should now be used for what, or with which applications parameters you can work with? There are several out there. To give you a short overview or a little bit of direction is when it comes to the surface texture and the quantification, the so-called S parameters, which are the areal functional parameters, are the most accurate one to use. Why is that? Because these parameters are the ones that are giving you more details about the area you are controlling or the area you are inspecting over a profile, for example, where a lot of information about the surface can be hidden. So these parameters itself can be divided into 4 different groups. The amplitude parameters, the spatial parameters, hybrid parameters, and functional parameters. So the amplitude parameters are the analog ones to the 2D parameters, which are assessed via height, nature, and form, and are also already well known in terms of like the SA or the SQ, which are the analog parameters to the RA or the RQ values. When it comes to the spatial parameters, they are derived from the autocorrelation function to obtain, for example, the preferred direction of the surface. Then we do also have the functional parameters. They are derived from the Abbott curve, and they are important to assess, for example, lubrication, the behavior or the adhesion of the surface itself. And the fourth ones are the hybrid parameters. They combine the height and the spatial parameters together. And on the right-hand side, you can see a table which can also give you an idea in terms of what kind of function you want to measure, which of these parameter groups have the most meaning or the most evidence to give you good information on that. And for example, if we take a look at painting and plating, you can see that the most evidence you're getting out of it are the amplitude parameters and the functional parameters. So the amplitude parameters are the analog ones to the 2D ones, and the functional parameters are the ones derived from the Abbott curve. And when it comes to the Abbott curve, when it comes to the functional parameters, and it comes to the Abbott curve, this is a direct function from, or the Abbott curve is also called the material ratio curve, and it is a direct function of the surface texture profile. So here, the areal material gives you a very wholesome way of the information of the core material, the core roughness, but also of all the valley depth. So, but how does white light interferometry works? In a matter of times, I will skip over this slide and directly go to our white light interferometry measurement system or how it directly works. So on the left side, you can see the basic components of a white light interferometer. So from a light source itself, which is in our case either a green or a white LED, we introduce light into the optical path. And The light then gets splitted into a beam, which is a reference beam, and this one is directed to a reference mirror, and into a measurement beam, which is then directed to the sample itself. Then both light beams are combined together at the beam splitter and focused with the camera. And there it forms an interference pattern. And from this interference pattern, the measurements or this interference pattern is translated into peaks and heights of the surface. And so a surface is measured. So with this technology, you have a technology that is universal for all application itself. So we have here, for all objectives, for all magnifications, we have the same high accuracy in set, so the same high vertical resolution. We can do fast measurements over large areas. We can also, with unique objectives, we can access difficult areas like vertical walls, like in the battery canisters. It is possible with white light interferometry to measure shiny and curved parts. It is also independent of the color or the material, and it's possible to measure transparent finishes or thickness of films. And the most important here is also it's non-contact, so you have no damage on the texture, on the sample itself you're measuring. So thanks a lot. And we are here for your questions.
Thanks, Sandra. We've got a couple of questions here. I think Roger may want to come on stage as well, and then we can see, who's best placed to answer this. Wonderful. Welcome to the stage, Roger. Just be aware before you begin speaking, you are muted. So I'll read the first question out from Peter, who asks, can your technology be used to quantify the size, distribution, and number of defects, like micro pits, for example, in DLC coatings?
Yes, I believe on one of Sandra's slides we discussed corrosion detection, the same type measurement, and automatic analysis could be used then to look for any surface defects. You can actually tell it how deep of the defect you want to detect, and then the size limit if you want to put a lower limit or upper limit, and do that analysis.
Okay, great, thanks. And nice general question here from Matt, who asks, what are the advantages of white light interferometry over other non-contact 3D methods such as structured light?
Oh, very good question.
Mm-hmm.
Structured light typically is like a fringe projection where it generates fringes over the whole surface.
Mm-hmm.
And the advantage they have is probably large. They can do a whole gear and compare it to the whole CAD model. White light interferometer or coherence, its advantage is it has better Z resolution. So we have sub-angstrom type resolution, no matter on the magnification, as Sandra pointed out. Plus, we have much better lateral resolution, which does change with magnification. But we're probably more in the nanometer type analysis, looking for these micro pits, looking for film thicknesses, where scanners are more of a rougher, hundreds of nanomicron type measurement.
Mm-hmm. Okay, got it. Thank you. There's a good question from one of our previous speakers here. Thanks, Ian. Over the last 10 to 20 years, there's been a significant development in surface measurement technology. What do you see as the development areas in the next 10 years?
I'll leave that one up to the product manager.
Right. Yes. Or there will be several ones. It is also depending in which area the optical or the measurement technologies are used. So one of the most important things is, of course, the speed, the area of measurements, and of course the resolution. So the main important topics over the past 10 to 20 years will also be the ones who are dominating the ones. So it's all about speed of measurement, area, and resolution.
Okay. Thank you very much, Sandra. In regards to time, unfortunately, I think we're going to have to move on now to our final speaker. Thank you both very much. Great presentation, great discussion of the technology here. Roger, if you don't mind, Peter has asked another question in the chat. Perhaps you can answer him there. But for now, we're going to move on to our final speaker, Dr. Nicholas Morris from Loughborough University. Dr. Morris is a chartered engineer and senior lecturer with over 14 years of experience in powertrain dynamics and tribology research. He specializes in tribodynamic simulations and experiments to address efficiency, wear, and NVH issues. He became a lecturer in 2016 and a senior lecturer in 2019 with postdoctoral research with the Lloyd's Registry International Institute for Cavitation Research. He serves on the IET Tribology Executive Committee and the journal Lubricants editorial board. There we go. I can see your slides. Dr. Morris, welcome to the stage. Please take it away.
Excellent. Thank you for the introduction and invitation to speak today, Sam. So, as Sam mentioned, my name is Nick Morris. I'm a member of academic staff at Loughborough University. And today I'm going to present some of the techniques, methodologies, and approaches that we have created to use to investigate electrical discharge machining with particular application to electric vehicle bearings. So the main aspects that I want to cover today are some of the fast methods we've used for screening different combination bearing technology lubricants for electrical discharge machining, like I said, particularly with application to e-motors in electric vehicles. Then we'll have a specific case study where we look at the role of conductivity on those bearings. And then in the second part of the lecture, we'll look at what's the role of surface roughness on electrical field strength and therefore propensity to electrical discharge. And then the very final thing that we'll cover is what's the role once a surface is damaged, electrical pits have formed on the surface. How does this again affect the electrical field strength and the propensity to ongoing electrical discharge events? So to start with, we'll just talk about the importance, which was highlighted nicely in some of the earlier presentations. Some aggravating factors for future electric vehicle designs are shifts from system voltage architecture from 400 to 800 volts, higher switching frequencies of pulse width modulation with the introduction of silicon carbide inverter technology, market competition driving new technologies and pushing the limits and envelope of what's possible, and general increase in e-motor size and power output. So on the right-hand side here, we've got a cross-section of a typical electric motor, and there's several reasons we'll touch upon here to describe where these voltages occur across the bearing which cause the electrical discharge. So we have inductive circulating currents caused by either geometric asymmetries or asymmetries in the magnetic field axially along the shaft, also things like material inhomogeneities. And these can cause currents to run along the shaft, through the bearings, around the stator and back through the bearing on the other side. Then we also have capacitive currents, and these are also called electrical discharge machining currents. And these result from the 3 phases of the passing through the windings not instantaneously summing to 0. And this causes an instantaneous common mode voltage between the rotor body and the frame. These common mode voltages change quickly with time, so we have a high rate of change of voltage with time, dV by dt, and this can help, or this means that we can drive high capacitive currents across the conjunctions that you can see here. So we have various different capacitive conjunctions between stator and windings, between windings and the rotor body, between the stator and the rotor itself, and then also across the bearing as well. So once we have these charge build-ups on the surfaces of the bearing, what can happen? Well, we can have resistive or static dissipative leakage of the current across the bearing. So the bearing is comprised of 2 surfaces. You have, or there'll be 2 surfaces in contact. So it'd be an inner race, rolling element, and then rolling element and the outer race. And in between that, we'll entrain a lubricant film. So if we have the lubricant film there, it has a fairly low conductivity. And as a result, you'll see a small amount of current leaking across that interface. When it's in the full film regime of lubrication, elastrohydrodynamic. If the voltage is high enough, then the electrical field strength within the lubricant film will exceed the breakdown voltage, the dielectric breakdown voltage of that fluid, and an electrical arc will form. And the electrical arc has a much lower resistance. So we have a low resistance electrical path formed between the 2 bodies, so inner race and rolling element, or rolling element and outer race. When this happens, we have a significant increase in the current flow between the surfaces, and in a fairly small area. So these Hertzian contact half widths here are in the order of micrometers, and then the current flow in the breakdown region will be a fraction of this area. So we're talking a sub-micrometer in terms of this discharge area. So we have high heat intensities, the heat per unit area from joule heating. And this can locally melt a small section of the rolling element or race surfaces. This can then cause for an electrical pit to form, and or a change in the material properties as it's quenched by the lubricant that is next to it. So we get this thermal damage to the metal surfaces of the rolling element or races, and that can also over time damage the lubricants as well. So some of the things that we've done here, we've created simple test rigs for fast evaluation of various different properties. So the test rig that you can see here has 2 bearing blocks which house a lubricant bath, rotor, bearing to apply a fixed load onto the shaft, which represents the rotor weight, and then also a disc which rotates with the shaft, so we can put eccentric masses on there. So why do we want these particular loads? So they're there to replicate the forces which act on a EV bearing. So a typical EV rotor weight will be between 80 and 230 newtons, so 8 kilograms to 23 kilograms, roughly, from what's out there in current technologies. So the bearings have to support that weight, but then you also have the acceleration of the vehicle, and the bearing has to keep the rotor moving with the vehicle as it accelerates around corners and decelerates and accelerates. And then we also have imbalances in the rotor, typically limited to about 2 G in millimeters per second, to prevent eccentric loading or significant eccentric loading of the bearing. And these e-machines can go up to roughly 20,000 RPM, but common urban, extra urban driving might be in the region of 7,000 to 10,000 RPM speeds. And so this test rig can go up to 9,000 RPM. We've scaled it. So this is the test rig there, you can see is much smaller than an electric vehicle motor. So it can be easily used by a single person. And the parameter that we kept the same to those predicted to be on the electric vehicle was the film thickness in the conjunction. And we'll cover why we did that in the next slide. So we used scaled bearings, scaled loads, scaled eccentric loads to replicate what's happening on an E-machine. So as well as the physical test rig, we also have a circuit level analysis, which includes the dynamics, so how the rotor moves with time based on the forces which are applied to it from the bearing and the loads. Tribology in terms of predicting what the film thickness is between each of the components, and then an electrical model to interpret what those film thicknesses means in terms of the capacitance formed between each of the elements, and also the resistance of flow, of electrical flow as well. So the dynamics includes Hertzian contact stiffness, and like I said, with the tribology, we're predicting EHL film thickness, both minimum and central film thickness. So we solve this as a nonlinear time varying RC circuit. Why is it time varying? Because these capacitances and resistances change with the film thickness. So as the film thickness changes, those electrical properties also change. So it's coupled in just one direction. The other thing that we also consider with the resistance of each of the contacts, so this is the contact between the outer race and rolling elements, and then this is rolling element to the inner race, and drive end and non-drive end bearing. And this is the resistance of the shaft in between. So the other thing that we include within this resistance is we switch between a resistance when we're below the breakdown voltage of the contact, which is comparatively high based on the conductivity of the fluids. And then we can, if the breakdown voltage is exceeded, then we move to the resistance of the arc, which is much, much lower. And as a result, we'll have a significant discharge of current across the contact. So through the use of the experiment and the model, we can understand how different parameters relate to each other and cause the damage that we see from the bearings that we examine at the end of the test. So this is some results that we could show just to give an indication of what we can see through the test rig. So on the left-hand side of the image here, we have a damaged bearing by applying the electrical voltage across the shaft. And this occurs in less than a day. I think this took 7 hours or something, continuous running at fixed speed. Then on the right-hand side is the same bearing type run under the same conditions, but without the voltage applied across the shaft. So we can run tests to investigate when electrical breakdown of the fluid films within the bearings would take place. And the crosses here are the experimental data points, and the lines show the numerical model data points. So there's a couple of things which are of interest here. So as expected, as you increase speed or decrease loads, the EHL film thickness will increase. And as a result of that, the electrical field strength in the contact decreases, and it means you require higher voltage to break the lubricant down electrically to overcome the dielectric strength of the lubricants. The other thing to notice here, which isn't immediately clear from the graph, is that to fit these lines to the experimental data, we had to use a dielectric strength of the lubricant, which was significantly higher than that provided on the data sheets. So I think it was alluded to earlier, but there's standards for measuring the dielectric strengths of lubricants. Now, these are measured with the electrode distance at 1 inch separation. However, the distance between the rolling elements and the races within these bearings is sub-micrometer, at the most several micrometers. So we've got orders of magnitude difference in terms of the standard test for dielectric strength. And it's well established that dielectric strength, when you measure it at different electrode distances, changes significantly. So it wasn't unexpected, but we wouldn't be able to use the standard value for dielectric strength of this fluid. But it's an interesting finding, nonetheless, to show that to fit this data, we had to use a significantly higher dielectric strength for the lubricants. And this is just to show some of the correlation between the model results that we can see, which we're not able to measure easily experimentally. So on the left-hand side is the condition when we haven't exceeded the dielectric strength of the lubricant with sufficient voltage. So we can see that we get very low. The blue line shows the current passing through the contact. So this is the static dissipative behavior. So we get extremely low. This is times 10 to the minus 12 amps. And we have the voltage across the contact on the right-hand side here. When we reach a high enough dielectric strength that we overcome the high enough field strength that we overcome the dielectric strength of the lubricant, then we create arcs, or in the model, it sees that as a low resistance contact. And we get these areas where we have a sudden discharge of electrical current. So you notice at the top here, there's no times 10 to the minus, this is just 0.18 amps. So we go from times 10 to the minus 12 to 0.18 amps. And so this current then is discharged between the surfaces. And it's in this condition, if I switch back to the previous slides, that we see these wear events taking place. These ripples that we see here are based on the vibration of the shaft and aligned to the ball pass frequency. So each time one of the rolling elements moves underneath the load, it provides a small kick up to the shaft, and a bit of additional force from that case, until the next ball or rolling element passes under the shaft and then gives it a kick. Each of those kicks create this vibration on the shaft. They slightly change the film thickness, slightly increase the field strength, and then we get the discharge that we see in each of these locations. So another study, one of the other studies that I just wanted to cover in today's talk is to look at the role of lubricants with different conductivities. So these were kindly given to us by Lubrizol, and we have 5 different lubricants. So we have a base lubricants. So base lubricants typically have a conductivity of something of the order of 1 times 10 to the minus 14 Siemens per centimeter. Then we have a very low conductivity lubricant, which is only a little bit higher than this in terms of conductivity, say 5 times 10 to the minus 14, and not commonly used for transmission lubrication applications. We have a low, medium, and high conductivity, which are typically used for transmission lubrication applications. And the way that these fluids have been formulated is that the additive pack is the thing that changes the conductivity. The base fluid stays the same throughout, and the viscosity characteristics are very similar throughout all of these, so that we can assume that the film thickness in the contact is very similar for all of these. So we conducted a similar breakdown voltage test to those that I showed on the previous slides. This is experimentally, and we can see that compared to the base oil, the low and very low conductivity additive packs correlates with a higher breakdown voltage, and then the medium and high conductivity additive packs correlate to a lower breakdown voltage than that of the base oil, if we take the base oil as a reference. Now, if you run these different conductivities, which vary from the additive, which vary from the highest conductivity of 1 times 10 to the minus 10 Siemens per centimeter to 1 times 10 to the minus 14 Siemens per centimeter, they're all very low conductivity fluids. For context, tap water will be about 1 times 10 to the minus 4. So we're getting on for 6 orders of magnitude less than the conductivity of water at best. So when you run these conductivities through the electrical model that I showed previously, you see almost no difference in terms of the voltage across the contact, which it sees. It marginally changes. So what I think we can say here is that the extremes, which is possible in terms of current lubricant additive pack conductivity, correlate to, and it's correlate, not necessarily causes, a plus or minus 10% change in breakdown voltage with respect to the base oil. And this is probably more likely to be as a result of not the conductivity and dissipative current leakage, but more likely a change in the dielectric strength of the film based on absorbed layers on the surface relating to the additive pack chemistry. So the last part of today's talk that I wanted to cover is, well, what happens if we change the surface roughness on electrical field strength, and using electrical field strength to indicate the chance of dielectric breakdown and arcing and in turn damage. And then what happens if we already have an electrical pit formed because we've had some unexpected condition which has caused a certain surface damage? Will that cause more EDM pits to form in future? So this is for a smooth surface, and this is a generic EHL model. So these blue areas here are the metallic surface where we have an idealized conductor. In the middle, we have an idealized dielectric, and the permittivity of the dielectric changes all the way across the film with the EHL fluid film pressure of the contact. So in this case, we can see that for the smooth surfaces, as we'd expect, the point where the surfaces are closest together has the highest field strength. And I've used a dimensionless field strength here, so it's just normalized to the smooth surface, and it's the same for all of the other figures. So it's normalized by the minimum film thickness and the voltage which is applied across the contact. So when you look at all of the figures, if it says 1, then that's exactly the same as the smooth surface between the minimum film thickness. If it's higher than that, then whatever's been added to the model, so the roughness, for example, or an electrical discharge machining pit, has either increased or decreased it relative to the smooth case, and what we would commonly assume as a typical value for when breakdown would occur. So if we apply a very smooth surface roughness, so this was measured with the Brooker-Emprey flex that we have here at Loughborough. If we measure a very smooth bearing surface, then it might have a roughness of tens of nanometers RA, and we can input that into the model, and we see that the maximum field strength still occurs at the constriction, at the EHL contact exit, and that the maximum field strength is still 1, so nothing's really changed compared to the smooth case when we have a very smooth surface roughness. Then we measured the surface roughness from an electrically damaged surface. So this was run on the test rig. We took apart the bearing, we measured it on the white light interferometer, and then we imported that line scan roughness into the model. So it's not exactly the same conditions, but it's a comparative representation of what happens. And so this scale now, instead of being to 1, this is now to 2. So anything which appears yellow on this figure is having about 1.5 to 2 times the electrical field strength of the smooth surface. So we can see once the surface has been damaged through fluting, for example, which is similar to the roughness of the surface we see here, the field strength in the contact increases, and the propensity to further electrical damage then increases. The threshold that the common mode voltage has to achieve to cause ongoing electrical damage decreases, in other words. And that's up to 2 times, this model indicates. But it's more to show the order of magnitude that can change, rather than this being an exact representation of the contact. So we can also get more significant features that can occur. So this would be an EDM pit that you can see on the figure up here. And if we take a cross section of that and allow the EDM pit to move through a representative EHL contact, we can see that that EDM pit on its own can cause a 2 times increase in the field strength with comparison to the smooth EHL contact that I showed on 3 slides back. So in conclusion, we've got a scaled test rig capable of reproducing electrical bearing wear and supporting model. And I'll show you some example data that we've used to investigate additive conductivity on electrical breakdown strength of the fluid film. And it shows that although it has a role to play, it's not significant in determining the breakdown voltage, and factors such as speed, load, which which relate to EHL film thickness are more important. We look at the magnitude of the electrical field strength as a result of legacy EDM pits passing through the contact. And we've shown perhaps something of the order of twofold magnitude in electrical field strength can occur. We look at how the electrical field strength, that the surface roughness has an effect in terms of increasing the electrical field strength within the contact if the surface is significantly rough, like that might occur from a fluted surface, but also that the maximum field strength where the dielectric breakdown is likely to occur moves. So in a smooth surface, it would be at the EHL constriction at the exit. In a rough surface, fluted surface, it moves to the individual asperities themselves. So lastly, I'd just like to thank some of the students and colleagues which have worked on this with me over the last few years. So Sam, Nikhil, Miles, Adrian, and Michael. So thank you very much for listening to the presentation today.
And thank you very much, Nick. Yeah, really interesting presentation. Lots to lots to think about there. I realize how much, or sort of how little I know about this specific area. We've got a couple of questions here, which we'll use to just sort of finish off our webinar today. First one from Jamal, who says, very interesting equipment use with a fundamental and simple design. My question is regarding the inclusion of wear debris in the lubricant. Will it affect the dielectric properties of the lubricant? This would be important when the test runs for a longer time.
Yes, very, very good question. So it depends on the nature of the wear debris, on its conductivity. Are they metallic wear particles? What shape are the wear particles? Are they platelets? Are they all of those things? I would expect it has some effect. Exactly what that is, I couldn't say. And they would probably be quite dissimilar to what they are in the bulk and what they might be instantaneously as they pass through between two surfaces at a small distance. Yes, it's an interesting area for future work, I think. What the wear particles are, nature of them. Yes, interesting points.
Yeah. Absolutely, thank you. And our final question today from our first speaker, Ali, who asks, how would the dissipation factor look like for the lubricants you shared with different additive packs? Would the dissipation factor be an important factor in EDM? If yes, how would the additive package affect that?
So the additive pack the conductivity of the additive pack for most transmission lubricants commercially available only changes by an order of magnitude, really. The extremes with a base oil and an oil which isn't commonly used for automatic transmissions. So within what's possible, the conductivity itself doesn't make a huge difference from what we've seen, because they're typically small or very small numbers.
Okay. Thank you very much. For anyone wondering, the attendance certificate link is now available. But I think now we are just a few minutes over our advertised time. So I'd just like to say thank you very much to all of our speakers today. Thank you all to everyone here for fantastic questions. Yeah, it's been a great event. With that, let's bring this symposium to a close. So thank you very much to Brooker for partnering with us for this event. We would not be able to do what we do without our partners. It's very much appreciated. To all the speakers who have put together their presentations, given up their time to present here today. Thank you very much for sharing. I think it's been a fantastic discussion regarding the tribology and challenges in electric vehicles. As a reminder, if you do want to see more of what we do here at Surface Ventures, please visit our website, surfaceventures.org. You'll see information about our upcoming events. You can see our archive of previous recordings. They're all available there. One thing I would like to highlight as well is our upcoming keynote on the 31st of October with two speakers, which you can see there. Please do go ahead and click on that registration link. That will be available on our website soon. As a final thing to highlight, we have our fortnightly newsletter, Modern Surface. You can read this on LinkedIn. If you type in Surface Ventures on LinkedIn, you'll be able to find us very quickly. And finally, I would just like to say, for those of you who are new to this, even if you've been to a few of our events, and you know someone else who would be interested in this, please, do spread the word about what we do. It'd be great for us to keep going, keep growing, excuse me, see new people here, and grow our audience, so we can keep running fantastic events. With that, thank you all very much. I hope you all have a great rest of your day. Goodbye.